Here is the next example. In this example, here is the given transfer function. H of s equal to 5 plus s, 100 plus s, 10 to the power of 5 over s square, 1000 plus s times 10,000 plus s. So here is that transfer function which is representing a system. Here we have four poles, s square, so there is a repeated pole at the origin, and two more poles, so it has 4 poles. Now Bode plots tells us that how this system behaves. Basically, this is a mathematical equation. This mathematical equation is representing a system. So Bode plot tells us that how this system behaves with respect to change in frequency. Now the step 1, what we need to do, everything write in terms of s plus 1. So what I'm going to do here, I'm going to pull out the 5 out, 100 out, so 5 out, 100 out, so it's going to be 1 plus s over 5, 1 plus s over 100. Same way you can pull out 1000 and 10 to the power of 4 in the denominator. Now the final transfer function will end up with h of s equal to 5 times 1 plus s over 5, 1 plus s over 100, s square, s 1 plus s over 1000, 1 plus s over 10 to the power of 4. Now these things are called corner frequencies. So this 500, s square over 1, 1000, 10 to the power of 4, these are all called corner frequencies. Corner frequencies are nothing but the frequency at the magnitude of the Bode plot is going to change its direction. Now when you convert this into HTB equal to 20 log 5. By the way, s is nothing but j omega, so I'm replacing s with j omega. So 20 log 5 plus 20 log 1 plus j omega over 5 plus 20 log 1 plus j omega over 100. So the numerators, we're going to add them together, denominators add them together, but you need to subtract them from the numerators. So basically the denominator is going to be minus. So you have s square, so s times s, so it is 20 log j omega plus 20 log j omega, so it's going to be 40 log j omega. So minus 40 log j omega minus 20 log 1 plus j omega over 1000 minus 20 log 1 plus j omega over 10 to the power of 4. Now how do you draw the plot? Now 20 log 5 is nothing but 13.97. So here it is, the magnitude does not change with respect to frequency because there is no frequency here. So that's a straight line, blue line. Next one is 20 log 1 plus j omega over 5. Okay, corner frequency is 5. It is increasing at the rate of 20 decibels per decade. So it's going to start at 5 up to 5, that magnitude is 0. Whenever you see a real part and imaginary part, real part is 1, in that case the magnitude is going to be 0 up to the corner frequency, and then it will have a slope of 20 decibels per decade. If it is a 0, then it is increasing. If it is a pole, it's going to decrease. So how did I get that 20 decibels per decade? So start at 5, okay, and 50. This distance is called decade. This distance is decade. 20 decibels is right there. This distance is 20 decibels. So that's how I found, I got the second point. So I took a ruler and draw a straight line that will indicate 20 log 1 plus j omega over 5. Same way 20 log 1 plus j omega over 100, the green line. Now minus 40 log j omega over 1. Here I don't have any real part, only imaginary part. Since I have only imaginary part, it's going to pass through the corner frequency 1, okay, but it will not bend at 1. It will continue on the other side of the corner frequency too. So that's how this is a straight line all the time. It will never be horizontal with x-axis. So if you don't have a real part, so in this case I don't have a real part, then the magnitude plot is always a straight line, always have a slope of depending upon either 20 dB per decade or 40 dB per decade. In this case, it has 40 dB per decade because it has a repeated pole. Now another one is at 1000 it will have another line at 20 dB per decade. At 10,000 another line 20 dB per decade. Now we're going to add them together. So the final line is yellow line. So here initially at 10 to the power of minus 1, what is the total magnitude? Here I have 14 plus 40. So this must be around 54 at that point. Magnitude is at that point 54. Now up to corner frequency 5, see you have only these two lines. Okay, so basically one line is decreasing, another line is constant, so the magnitude will follow this green line. Okay, another way of saying it is at 10 to the power of 0, what is the magnitude? At 10 to the power of 0 magnitude is going to be 14 because this value is 0. So now you have 2 points, take a ruler, draw a straight line. Don't stop it at that point, stop it at the next corner frequency. The next corner frequency is at 5. Now at 5, now I already added this 14, so don't worry about that. Now this line has 40 decibels per decade as a corner as a slope, and this line has a positive, the black line has a positive slope of 20 decibels per decade. So what happened? The resultant will be 40 minus 20, so it will have only 20 decibels per decade as the slope. So start from 5 up to 50 right there, take another point, and so here this height must be 20 decibels. That's how I got it. But continue up to the next corner frequency. So here I have 20 going up positive, another 20 positive, but 40 negative. So what happens? They cancel out each other. It's going to be a straight line, and at the end you're going to add up another 20, add up another 20. So here you will have, so let me write down here, slope is 40 dB per decade. Here it is 20 dB per decade. Here it is 0, here it is 20, here it is 40 dB per decade. That is the slope of the final line. Now to draw the theta line, theta equal to tan inverse of 0 over 5 plus tan inverse of, because tan theta is nothing but imaginary over real. So imaginary for constant 5 is 0. Okay, tan inverse of omega over 5, tan inverse of omega over 10, sorry, omega over 100 minus 2 tan inverse of omega over 1 minus tan inverse of omega over 1000 minus tan inverse of omega over 10 to the power of 4. Okay, now here this value becomes 0 because tan inverse of 0 is 0. At the same time, here I have 2 times because it's a repeated pole. So now imaginary over real part is 0. So tan inverse of omega over 0 is, it's 90 degrees, 90 times 2 minus 180. So if I simplify that equation, I end up with theta equal to tan inverse of omega over 5 plus tan inverse of omega over 100 minus 180 minus tan inverse of omega over 1000 minus tan inverse of omega over 10 to the power of 4. Now I put omega value, I chose this omega value, this is the initial 10 to the power of minus 1, make sure you have that initial, and also 1, and then make sure you have include every corner frequency. Okay, so at 10 to the power of minus 1, actually this is approximate value because I didn't include this value. So tan inverse of 0.1 over 5, very close to 0, not exactly 0 though. So 0.1 over 100 less than this value. I think this value is around 1 degree. This value might be like 0.01 degree, and these values are negligible. I mean 0.1 over 1000, 0.1 over 10,000. Okay, so at 10 to the power of minus 1, approximately that value is minus 180. At 1, minus 168, minus 135. These are all approximate values but very close to the real values. Okay, so when you draw the phasor plot, make sure start at -180 and upwards -1. I mean, it's up to you how do you break down. I'm choosing 45 degrees each, that distance. Okay, so here is the phasor plot. Now we need to find gain crossover frequency and phase crossover frequency. Here the phase crossover frequency, phase is not crossing anywhere 180 degrees, so I don't see any phase crossover frequency, so I would say phase crossover frequency is none. Gain crossover frequency is where the gain is crossing the 0. So here it is crossing right there. I would say 1, between 1 and 2, but I think I chose this as 1 or 2. Gain crossover frequencies, I chose that as 2. It's approximate value, so I chose that from the graph. Now the phase margin is nothing but, so make sure that you draw these two graphs one under another. I'm assuming these two lines are the same. So if you look at here, this is the, okay, here it is. So find out what is the angle there. I think this value is around -155, something like that. Okay, or maybe 140. These are all approximate number anyway, so I chose that as -155. So the phase margin is -155 -180 degrees, so I'll end up with 25 degrees. That is the phase margin. Gain margin is we don't have any gain margin here in this example. Okay, so basically the Bode plot help us to find the behavior of a system. So behavior of a system, that system is represented by this mathematical equation. It helps us to find out the behavior of a transfer function in with respect to the frequency. I will stop it here. Thank you.